Thank you very much for coming. I'm going to talk to you today about the Florida current, and we'll discuss something about the transport and variability and how accurate the measurements that we make are. This is work that I do in collaboration with Rigo Garcia and Molly Berenger, as well as a whole host of people who participate in the cruises when we collect this data. So today we'll talk a little bit about boundary currents that are observed as part of our Western Boundary Time Series project. We have three main currents in this region. There's the northward flowing Florida current, which is carrying about 32 sphere drips. There's a smaller current called the Antilles current that's flowing northward just east of the Bahamas, carrying about 5 sphere drips. And there's the southward flowing deep western boundary current. It's flowing at depth around 1800 to 3600 is where the core of the flow is. It's flowing southward east of the Bahama Banks. Why do we care about these currents? Well, we care about them because the bulk of the upper and lower limbs of the meridional overturning circulation are carried by these currents at this latitude, and we know from numerical model studies and other work that variations in the MOC have significant impacts on things that we care about as a society, including precipitation patterns and air temperatures. Part of the observational programs that are used here, we use a wide range of different kinds of equipment. The program started in 1982. It was called STAX in those days, and it has gone through several generations over the intervening time period. The submarine cable and the Pegasus were used in the beginning. Dropzones, which you see here in the lower left, were introduced in the 1990s. CTD LADCP were introduced in the 2000s. Historically, going back further, you had dropzones used in the 1960s and 70s. There was some cable work done in a preliminary way in the late 60s and early 70s, and the first observations of the Florida current here overall were back in the 1880s, just after the Civil War, when a gentleman by the name of Pillsbury invented his own current meter to make the first measurements of the strength of the Florida current. We do most of our measurements at the 9 sites that are indicated by the blue stars in the map. The cable location is indicated by the red line. So what does the Florida current look like? Well, here you see a vertical section of the Florida current that is from the Pegasus sections that were collected in the 1980s, and this is the meridional velocity. You see the strongest velocities are on the west side of the straits up in the shallower waters, but the flow is all northward at all depths throughout the entirety of the straits. Basically, the Florida current is filling the straits. The volume of water, the 32 sphere drips that I mentioned, is sufficient to, if you could redirect it into a large stadium like Marlins Park indicated here, it would fill the stadium to overflowing in less than a second. It's a vast amount of water. The variability of this is believed to be mostly locally wind-driven when you're talking about changes that are occurring over the 4 to 10 day window. And at longer periods, the variability is thought to be more based on wind patterns across the entire Atlantic basin at this latitude. We've collected historically up to 450 sections of velocity across the Florida current since the mid-1960s. As I mentioned earlier, the early sections were collected at 26 North, but basically from the 80s to the present, the bulk of the data was collected here along 27 North. We have a time series of all of the data going back to the 1960s, shown in the top panel on the right. And to illustrate the agreement between the ship sections and the sections collected, or the data collected by the cable, you have the lower panel on the right, which highlights one particular year, 2008. And you can see that the symbols from the ship sections are laying on top of the cable measurements quite well. All of the measurement systems indicate that the mean transport of the Florida current is about 32 sphere drips at this location. How well do these different data sets agree? Well, this top panel here illustrates the correlation between the ship sections, whether they be Pegasus, lower ADCP, or dropzones, and the cable. And what you can see in the top panel is the correlations were quite high in the beginning. They got a bit lower in the mid-90s, and there were some problems with the cable, because actually at that time the cable was a actively used telephone cable, which induced some noise into the system. And then in the 2000s, things have improved significantly. We're back up to correlations around 0.8 or 0.9 most years. The RMS differences similarly were low in the early 80s and are low again in the 2000s, and got a bit higher during the time period where the active phone line was being used. How much variability is there in the cable? Well, the timescales really drive all of this. You saw the transport changes of 5 to 10 sphere drips. We see here, if we break it down into periods, that in the first time period, 1982 to 98, when the cable was used continuously, roughly a quarter of the variance is at periods less than 30 days, and 40% of it's in periods of a month to 11 months. Only around 11% is in the annual timescales, and at longer periods there's a bit in the kind of 1 to 3.5 year timescale, and a little bit longer than 3.5 years. In the 2000 to 2014 period, when the cable got restarted, the percentages are quite similar. So basically we don't see much change in terms of the distribution of variance in different timescales. So I want to focus today a lot about the accuracy of the Florida current estimates. Really, if you don't know the accuracy of your measurement, there's really not much point in talking about the measurement at all. There's two different kinds of accuracy we're going to talk about. We're going to talk about measurement accuracy, which is how precise is your measurement tool itself. And we're going to talk about statistical accuracy. Essentially, if you think of trying to get an annual mean temperature in your backyard and going and making only 2 measurements in the year, and both of them were in July, you would not get a very accurate measurement, and that's what we're talking about, statistical accuracy. Both kinds of errors are important. We'll talk about the statistical accuracy first. So the long continuous cable record from 1982 to 98 can be used to evaluate what kind of statistical accuracy we can get from having a limited number of samples. So the red dots in the panel that you see here are a Monte Carlo simulation where we've gone into the continuous record and said, okay, let's try and see how good of a monthly mean we would get if we had a limited number of samples. So for example, we'll go in and say, if we had only 5 measurements over the course of the 1 month, what would the mean of those 5 measurements be? How does that compare to the true mean for that month? If we repeat this 10,000 times using our long record, we get an estimate of the accuracy one would have based on the limited number of samples. You can do the same thing for an annual mean, 3-year mean, or a 5-year mean, which are the other colored symbols that you see in this plot. Basically what you see from this is, if you want a half sphere drip error bar on your estimate of the Florida current for a month, you need 20 samples in that month, which is a huge number. It's pretty much impossible to do unless you have a continuous record. You just don't have the ship time to do that kind of thing otherwise. Similarly, you get out to the point of needing between 40 and 50 samples if you want to do this for an annual mean or a 3-year mean. So you need a lot of samples when you have as much high frequency variability as we have in the Florida current. This all assumes that the distributions are random in nature. So if you, again, using that simple example I mentioned a moment earlier, did your 2 measurements or your 5 measurements all in July and you were looking at an annual mean, that would be worse than this. These are kind of estimates based on if you have a random distribution. We can look at more than just determining means for a month or means for a year. We can also look at how well can you extract an annual cycle, for example, in the same way. So the top panel here shows a simulated 100-year cable record based on assumptions about the amount of energy in different timescales that come directly from our measurements. So if we have an annual cycle of the observed magnitude and interannual variability of the observed magnitude and subannual noise of the observed magnitude, you get the black line. And eventually, if you wanted to talk about an annual cycle, which is the blue line in the top panel, you would need to somehow average a certain number of years to get from the black to the blue. And the bottom panel here illustrates how many years worth of data one would need in order to do that. The blue line in the lower panel is if you're using the raw daily values. Pretty much no one would ever do that. You'd always use a 30-day or a 60-day low pass of your daily measurements. Nevertheless, what you can see is you need 7 or 8 years of data in order to get out to the point where you're starting to get down to the half a sphere drip sort of an error bar. You really need a lot of data in order to get your error bars down on the annual cycle when you have the annual cycle representing only around 10% of the total variance. So in 2001, there was a paper by Behringer and Larson who used the first 16 years of the cable data to illustrate an apparent change in the annual cycle. And in this plot here, you can compare the blue dashed line and the magenta dashed line. And what you can see is those two looked very different. One looked semi-annual, the other looked annual. And in this paper, they explored why that might be. When we had another 8 years of data after the program restarted in 2000, we were able to get the 2000 to 2007 data, which is shown in red. And you see that that's yet again different from the others, which really brought us to question whether this was a question of statistical noise or not. And in fact, if we use the error bars that I just showed you from the annual, for determining an annual cycle from a time series like this, we find that none of these are statistically different from one another. This is all just aliasing of other timescales into your data set. The black line illustrates the annual cycle if you use all 25 years. Now, pay attention to the fact that the scale on this figure goes from 3 sphere drips to 3 sphere drips, and we will now add the most recent 6 years and the annual cycle that comes from that. And in the panel that you see that has just flown in, you'll see that this vertical scale on the plot had to be extended down to -5 because the annual cycle one gets in the most recent years is radically different once again from all of the previous time periods. And again, this is all within the expected statistical noise that one would see. The black line in this plot, which is now using all of the data for 32 years, is extremely similar to the previous one. So once you get out to the point where you're getting about 25 years of data, things become robust. But until then, you have a lot of aliasing of others' timescales. Shifting over to measurement accuracy now, we have 3 measurement systems that we use to estimate the velocity in transport in the modern era: cable, lowered ADCP, and Dropzone. While statistical accuracy that we were just discussing is independent of the measurement system, the measurement accuracy depends on which system we're talking about. There's kind of 2 ways to really get at and talk about measurement accuracy. You can get at it by going to what's called first principles, actually looking at the accuracy of the constituent parts of the measurement. This is considered better, but it's also very difficult. And the other way that's commonly used is looking at the measurement system against something with a known accuracy. It's easier, but not as rewarding or not as robust. We'll talk about the accuracy of the Dropson measurements first here, and we're going to end up in the long run discussing a bit of both of these techniques for getting at measurement accuracy. So the Dropson is a very simple measurement. It is an instrument package with a GPS installed in it, and there's a small picture of it here. And you drop this instrument. It has a GPS fix where it starts. It sinks at a constant rate, as illustrated in the lower panel. When it gets to the bottom of the ocean, it drops the weight, comes back up to the surface where it reacquires the satellite measurements. Because it's at each depth for a constant and equal amount of time, this essentially gives you a measure of the vertical average horizontal velocity. Really then, because it's such a simple measurement, all you really need to know is the accuracy of the start point, the end point, and the time in between. Well, GPS accuracy has changed over time. Prior to the year 2000, there was something called Selective Availability that was installed, and that intentionally made data worse. The top right panel, or the top right figure here, shows a time series of GPS locations from a GPS antenna that was fixed on a vessel tied up at the dock for a day and a half in the early 1990s. And what you can see is even though this data that I'm showing here is 5-minute averages, so it's removing some of the noise, Nevertheless, the RMS error was around 24 meters. So it's quite noticeable, the amount of error that was introduced by selective availability. If we do something similar, here in the lower right, we show 6 hours of GPS data from an instrument fixed to a structure here at the lab. What you can see is a lot less variability. In fact, the RMS error is only 1.4 meters. So it's more than an order of magnitude better in terms of the accuracy. If we take these location errors and translate those into the equivalent velocity errors, we would get 6 centimeters per second for the pre-2000 time period and 0.6 centimeters per second after the year 2000. Now, this is not the only place where GPS accuracy comes into the issue, because when the dropzone returns to the surface, it doesn't instantaneously collect GPS information. It takes a certain amount of time before it reacquires the satellite signals. This is a standard and well-known part of the process with dropzones, and we try to correct for that based on tests that we've done. And here in the top right, we show tests of how long it takes to reacquire the satellite signal when the dropzone has been underwater and invisible to the sky for a certain amount of time. And the black line here indicates that essentially this is a small feature at short casts. We're looking at 4 to 5 seconds. At longer casts we might be looking at 20 to 25 seconds, but during that entire 5 to 20 seconds the instrument is moving at the speed of the surface waters, so that is biasing the vertical average towards the surface value. We correct for this, but we cannot correct perfectly. The scatter around this line gives us a measure of how accurate we can make that correction. In this case, the RMS scatter of these measurements is 7 seconds, which translates to a velocity error of around 0.5 centimeters per second. In our analysis of the dropzone accuracy, we also considered other potential sources of error, such as small variations in the sinking or rising rate, which would bias potentially the measurements. Turns out that's less than 2.5% when we testing a dropzone with a pressure gauge attached to it. And we also considered the impact of small differences between the sinking and rising rates themselves, which could also induce a bias. We made estimates of these error sources, and they're very, very small in comparison to the other terms. So essentially what we can say is that the two non-negligible sources of error, the GPS accuracy and the accuracy of the reacquisition correction, are independent of one another, and if we combine those two first principles sorts of accuracy estimates via a square root of the sum of squares, we can get a overall accuracy of the dropzone velocity measurement, which is 0.8 centimeters per second. This value is post to year 2000, so after selective availability was removed. The LADCP and the cable measurements that we also use to measure transport are much more complicated, and it's really impossible to do those via first principles. But happily we can compare them to the dropzones now that we have a good error estimate for the dropzones. Start with the LADCP. The top right panel here shows the mean northward velocity, blue or black lines, and the standard deviation of those, the blue crosshatch or the gray shading, for the dropzones in black and the LADCP in blue. This is just to show you that the two different measurement systems are measuring essentially the same thing. We wouldn't expect perfect agreement because there's on the order of 150 dropzone cruises, and there's only around 45 LADCP cruises. We have done, however, 22 direct side-by-side measurements where we did a dropzone cast immediately at the conclusion of an LADCP cast, and we can plot those against one another, which you see at the lower right. The agreement between the two is quite good. The RMS difference for the 22 measurements was 3.8 centimeters per second. This value should be a combined estimate of the two error bars on the two systems, because the dropzones have their own errors and the LADCP have theirs. So we now get to we can go estimate the LADCP accuracy using the same square root of the sum of squares technique but in this case solving for the LODCP accuracy given the fact that we know the combined and the dropson. If we do this, we get a final answer of 3.7 centimeters per second as the accuracy of the lowered ADCP, which falls roughly in the middle of historical LODCP accuracy estimates and should be a pretty robust measurement accuracy. Now, ultimately, we want to get at transport accuracies of the Florida current, not just velocity. So somehow we have to go from the velocity at the 9 locations, illustrated in the map in the middle on the right here, to estimates of the transport across the entire basin. To do that, we have 5 more different sources of error that we'd have to consider. Extrapolation from the shallowest station to the coast, interpolation between the 9 stations over a non-flat bottom, horizontal resolution, i.e. basically a question of whether 9 stations is sufficient, removal of tidal signals, because of course the tides are changing as we're going across and taking the section, and we don't really want to look at the tide transports, we want to look at the bulk transport of the Florida current, and finally the asynopticity of the observations, i.e. the fact that it takes a certain amount of time to go across and the ocean can be changing during that ship section. We see here that the typical lowered ADCP section takes 12 to 14 hours, whereas the dropson takes only 6. So asynopticity is worse for lowered ADCP than it is for dropsons. But all of the other terms are the same, regardless of which measurement system we're using. The first 2 items in this list are both very small, so for time I'm only going to focus on the other 3 here. To evaluate how well the 9 stations capture the transport, we took 19 high-resolution shipboard ADCP sections across the strait and subsampled them to only the 9 bins closest to the 9 stations. What you see in the lower right here are the transport per horizontal bin as you go across the straits from using only the 9 stations or using the entire full resolution. The top example is the smallest difference between the 2 calculated transports. The bottom is the largest. Essentially what you can see is you can barely tell the difference between these lines, which is therefore not surprising that the RMS difference between these various sections in using the only 9 stations is 0.2, which means that the scientists involved in picking these 9 stations out back in the 1980s did their job quite well. Talking about the transports, or excuse me, the tides, in the 1980s, when STAX was going on, the scientists put out a series of current meter moorings and some tide gauges, and using a combination of those data, they were able to calculate the barotropic tide constituents for the Straits of Florida. Essentially, everybody who's worked in the Straits since then has used those same constituents that were calculated by Dennis Mayer and colleagues. Of course, they're not perfect. No measurement is perfect. So we tried to come up with a way to estimate what sorts of inaccuracies might be involved in these tide corrections. We did this by calculating tide constituents from 2 modern pressure gauges that are located on either side of the Straits of Florida for a few years, starting in around 2008. If we use the tide constituents from those and we calculate the transports from those sets of tide constituents, we get the transport time, or the velocity time series that you see here in this panel. Essentially, these translate into transport inaccuracies of 0.5 sparedrops, which is what we will say is how accurately we think we can remove the tide transports from the overall transport. Finally, the largest source of error, or the most difficult source of error to estimate, is the asynopticity. Really, to do this properly, you'd need to have 9 moorings, 1 at each of the 9 station locations, and then you'd need to go into the continuous time series and select the measurements now for this instrument, 2 hours from now for the next instrument when we arrive there with this ship, 2 hours after that at the next instrument, and so on. Of course, that's not practical. So the best technique that we came up with for estimating how large the asynopticity errors might be is to look at the difference in transport between the 2 days when lowered ADCP sections are going on. So they always transition from one day to the next. So to get an estimate from the cable data of how big the transport changes are from one day to the next, which is illustrated in the bottom right panel. Essentially, for the 45 cruises that we have, this ends up being an RMS change of around 1 sphere drop. So we will have to use that as the lowered ADCP asynapticity error. Since the Dropzone cruises take about half that length of time, we will assume that the asynapticity error is half as big, 0.5 sphere drops. It's not particularly satisfying, but at the moment, with the data that we have, it's the best estimate we can make. So combining together all of these different sources of error, we get the table that you see here. And you see that the final answer for the transport accuracy for the Dropzone is 0.8 sphere drops, and for the lowered ADCP it's 1.3 sphere drops. If we look at the Dropzones prior to selective availability, the numbers that you see in parentheses, the Dropzones are also accurate to 1.3 sphere drops in the pre-2000 era. Essentially, these 0.8 and 1.3 sphere drop error bars represent only 2.5 to 4.1% of the mean 32 sphere drops of the Florida current. So these are really very, very good error bars. And we can feel confident that we're getting an accurate estimate of the Florida current with either system. Also exciting about this, because we have these two different systems, each of which has been used to compare to the cable, we can use these two error bars to try and back out a cable accuracy as well. As I mentioned earlier, we have on the order of 150 Dropzone cruises and around 45 LADCP cruises. Many of the Dropzone cruises have been used for calibrating the cable data, which means they're not independent. If we select out only those Dropzone sections that were not used for calibrating the cable, we have 44 sections that are not used. And the LADCP sections are all independent because they've all only been used for evaluating but not for calibrating the cable. If we do the RMS differences between the independent Dropzones and the lowered ADCP, we get 1.9 sphere drops and 2.2 sphere drops respectively. These estimates these RMS differences are larger than the errors, the estimated error bars that we have for those two systems, Dropzone and LADCP, which is to be expected because the cable must have its own error bar as well. Similar to how we got at the LADCP error earlier, we can reverse these square to the sum of the squares to get an estimate of the cable error that must go into them. If we do that, we end up with, using the Dropzone's value, we get a 1.7 sphere drops. Using the lowered ADCP, we get 1.8 sphere drops. So it's exciting that we get basically the same answer for these two independent systems. We'll use the number 1.7. I don't think there's any difference between the two in a statistically meaningful sense as the accuracy of our Dropzone or our cable daily estimates. Now, for doing climate studies, an error bar on a daily estimate from the cable is not all that valuable. Really, you would like to know how accurate is a seasonal mean or an annual mean. In order to do that, we need to know how much of that 1.7 sphere drops that we just discussed is random and is reduced by doing time averaging, and how much of it is not. In order to figure that out, we took a look through our large database of Dropzone cruises, and we identified cases where the Dropzone cruises were collected close together in time, starting with time gaps of 3 days out to 11 days. This gave us between 30 and 60 pairs of sections that are separated by spans somewhere between 3 and 11 days. If we take a look at the scatter plots and the histograms of these, we find that the errors look like they're becoming independent within about 10 days. So that would mean that in a 365-day year, we would have approximately 36 10-day periods in a year. And so if we do a square root, if we divide 1.7 by the square root of a 36, we'll get 0.3 sphere drops. So we would say that the measurement accuracy, therefore, of an annual mean Florida current is around 0.3 sphere drops. With the daily data, if we have continuous measurements, the statistical error bar for doing an annual average is going to be negligibly small. So the total error bar measurement plus statistical for an annual average Florida current estimate would be around 0.3 sphere drops, which is only 1% of the mean value. With the climate scale, time scale, with the climate timescale signals being around 1 sphere drip at interannual and longer timescales, these results indicate that while we don't have a huge amount of resolution, we should be able to observe reliably these 1 sphere drip errors, or these 1 sphere drip signals when we have 0.3 sphere drip accuracy. So to conclude, the daily cable observations are accurate to within around 1.7 sphere drips, and the decorrelation length scale of these errors is about 10 days. Dropzones and the LADCP can provide estimates of 0.8 and 1.3 sphere drips respectively in the modern era, so we can get very robust estimates of the transports of the Florida current. The annual average of the Florida current can be determined to within around 0.3 sphere drips. The percentage of Florida current variance associated with the annual and longer timescales is quite small, so to get meaningful estimates of a mean annual cycle, many years are required. Now that we're out beyond 25 years, I think we're finally getting robust annual cycles, which are not heavily aliased by the other timescales. Without that, if you have a situation where you have a really small percentage of the total variance in the annual cycle, you need a lot of years. And final point that I'd make is that if you're not carefully considering both measurement and statistical accuracy in your analysis, the results may not be as meaningful as you'd like them to be. So thank you for your attention. If you'd like more details, I can point you to the 2 papers that are listed here, and I'd be happy to take any questions. Thank you very much.